another applied regression class. Today we're starting chapter 3. Of course, I call this multiple linear regression in overview. In the outline today, I'm going to walk us through specification of multiple linear regression model. I'm also going to walk you through how ordinary least square approach work in a multiple linear regression model. Then how do we make inferences in linear regression model in general? That will be in the focus today. Uh, I think I'm first gonna have a recap. You know, how do we actually find ourselves doing multiple linear regression? Initially, in this class, I walk you through how we can characterize relationship between one explanatory variable and a response. But let me tell you this. We find ourselves in a world where at times a response variable may be related to more than one variable. And that is the reason why we want to focus on multiple linear regression, situation where we are trying to investigate relationship between a response variable and more than one explanatory variable. Of course, everything will start with specification. I remember the other time, you know, using this statistical framework, we normally begin with a model specification. So when we're working with simple linear regression, situation where we're trying to look at relationship between a response and one explanatory variable, we specified a mean function. The mean function, uh, you know, then was expectation of y given s equal the beta naught plus the beta 1s. So this is situation, this is only when we have one explanatory variable. Now remember, I also specified the variance function, but I wanted to take a look at 3.5. The 3.5 is an extended mean function. So if you take a look at what you have in 3.5, we are extending that to situation whereby we have more than one explanatory variable. We got x1, x2, up to xp. So in this situation now, the number of explanatory variables that we got is actually, I'm assuming we got p numbers of that. Okay, so at times we may actually want to figure out the average value of GDP or giving some economic variables, not just one. That's exactly what you're seeing is 3.5. Whenever an average is involved, of course, there's always going to be a variance. So the variance function, the variance of y given s, x in this case is x1 up to xp, is actually going to be sigma squared. If I want to make a decision, or if I actually maybe I want to take a decision regarding the relationship here, the parameters in my model need to be estimated. With with multiple linear regression, we're going to have a lot of parameters that will be estimated, and because of that, in order not to get into uh, in order to avoid mathematical complexity, I think I'm actually going to walk you through how this can be achieved using matrix algebra. So let me prepare your mind. In statistical framework, we borrow a lot of ideas from mathematics. So because a lot of parameters will be involved, here I'm going to have the beta naught, the beta 1, the beta 2, up to beta p. I'm also need the variance to be estimated. I got a lot of parameters to be estimated. And because of that, I think I have to use an approach in math that will enable us to simultaneously estimate all these parameters. Okay, so today we got a lot of theoretical stuff that I'm going to review with you, and you need to understand that because you don't want to be at the mercy of at least you want to know what is programmed, what formula is programmed behind the scene, in case you actually want to make use of software. So now what I'm going to do using the idea of matrix algebra now, because we got a lot of parameters involved, I can actually call, if you take a look at this guy, I'm actually going to say I have a beta, and that beta is a vector, and it contains beta naught, beta 1, up to beta p. So I'm trying to specify the parameters of interest. And of course, there's something I also want to show you. We have two ways of presenting the mean function. I'm going to show you how we present a mean function in a scalar way and in a matrix form. Why do I need to show you in a matrix form? Because we actually want to use the idea of matrix algebra. Matrix algebra because we got a lot of parameters that are involved. Now, take a look at this. This guy is a mean equation for multiple linear regression. But if I want to write that in matrix form, I'm just going to write this. Where my beta is actually this guy here. That's my beta. My beta is a vector. Okay. So is there anyone who doesn't understand 3.7, equation 3.7? Okay. Equation 3.7 is actually telling us how we can write mean equation, okay, for multiple linear regression, both in classical form and in matrix form. Okay, so if that is clear, the approach that we use in simple linear regression in estimating parameter, we're also going to use the same approach in multiple linear regression. And what is the name of that approach? We call that ordinary least square. The ordinary least square approach was actually used to figure out, okay, to estimate the parameters in a simple linear regression model. We're also going to apply that for multiple linear regression model. All what I need you to do is to pay attention because what I'm going to be unfolding today, they are mathematical somehow. Okay, now I need you to take a look at equation 3.8. Equation 3.8 is a way to present the mean function of multiple linear regression in a matrix form. X is called a design matrix, and that very X, okay, has a lot of features. It's not one. Then beta is also a vector, beta 1, beta 2 up to beta 0 up, beta 1 up to beta p, depending on the numbers of features or explanatory variables we're talking about. Now, because this is going to be a matrix, every matrix has dimension. Then I want to walk you through. If we specify a model, I'm going to show you how the model is going to look like. this is going to be the model y equal, okay, y equal x beta, okay, y equal x beta, okay, plus the error, okay. This is the way the model is going to look like, okay. That is the model. If that is the model, if I take the expectation, which means if I find the mean, that will give me equation 3.8. Why do I have equation 3.8? Okay, taking expectation of both sides, the expected value of error equal to 0. Okay, you remember under assumptions, the assumptions underlying the use of simple linear regression model, they are also going to be repeated in a multiple linear regression model. Okay, so the model is y equal x beta plus the error, and y is going to be a vector, s is going to be a matrix, the beta is going to be a vector, and error is going to be a vector. Okay, so this is where it's going to be. What is y? Okay, we take a look at y. Y is going to be n by 1. N by 1. I want to talk about the, what is it called? The dimension. It's going to be n by 1. Okay, when I talk about n by 1, okay, like this is what I'm trying to say. I have the model. I got the model to be y equal x beta plus the error. Okay, this guy. Okay, because I'm going to have y1, y2 up to yn. This is going to be n by 1. Okay, n number of observation by 1. Okay, this guy also going to be e1, e2 up to en. The dimension of the response is also going to be the dimension of the error. Okay, the beta. Okay, the beta is beta 1 or beta naught until you get to that. Okay, and if you take a look at what I have here, how many rows do I have? Okay, p plus 1. Okay, if you take a look at that. So this is p plus 1 by 1. Okay, the numbers of row, or if I want to go by 1 row by p plus 1. Okay, 1 by p plus 1. Why is it p plus 1? Beta 1 to beta p is p. The plus 1 is the beta naught. Okay, and if you want to call that beta naught, if you want to call that, so I'm actually going to have this, the way that I'm going to call p plus 1 by 1, whichever way you want to call that. Then x, this particular x is going to be a design matrix. We call that design matrix, where in the we're going to have x0, x1, x2 until I get to xp, and of course this is going to be 1 1 1 1 up to that. We're going to have a constant. We're going to have some values here under x1. No, that would be data, okay, until you get to that. So that's going to be a design matrix. Okay, so that is exactly what I'm trying to say. So if we're trying to we're trying to tell the world, okay, it's a component in this model. Is either going to be a matrix or it's going to be a vector. Okay, and we can also figure out what the error is. Okay, just like the same way we did. The error is going to be a gap. Okay, a gap. Y minus the model, the mean in the model. Okay, that's going to be error. Okay, and we're also going to have that expectation of the error is going to be 0, and the variance of the error. Now, the difference between this and simple linear regression, in the case of the variance of error, in simple linear regression, the variance of error is just sigma squared. But in a multiple linear regression, it is sigma squared identity. Okay, so I'm going to write something now. Okay, when I say sigma square identity, okay, when I say sigma square identity, the identity n here means is a square matrix, and if I have 2 by 2, it's going to be 1 0 0 1. Okay, this is for 2 by 2. If I have 3 by 3, 1 0 0 0 1 0 0 0 1, and so on like that. Okay, so in the case of multiple linear regression, the variance of the error will be sigma squared identity. But in the case of simple linear regression, it's just going to be sigma squared. Okay, now we're also going to have assumption on the error. Of course, I told you the other time, a model is as good as assumption putting into a model situation where this old, where the expected value of error equal to 0 given the design matrix X, and the variance of error given the design matrix X is sigma square identity that I'm actually going to call a constant variance, then I can say that error, okay, the error given the design matrix X follow normal distribution with a mean of 0 and the variance sigma square identity. Okay, so just wanted to take note of that. Okay, now I want to move into ordinary or least squared. Okay, how how do I derive the formula that I'm actually going to use to estimate the regression parameters in my model? Because before I'll be able to make a sense of what the relationship is going to be, the parameters in the regression model need to be estimated. Okay, so because we're using the least squared, okay, because we're using the least squared, we actually we're going to estimate regression parameters with the motive of drastically reducing the sum of square error. Now I need you to pay attention. Take a look at this guy. That's a sum of square error. Okay, that's a sum of square error. This is why this is predicted. Okay, you know, I said something the other time. I said the mean function in a multiple linear regression model. Okay, okay. I said it is actually this guy. If this is the mean, I'm talking about in matrix form. If this is the mean, okay, then I'm trying to say if I want to figure out the error, there's going to be y, the original y minus this guy. The original y minus this guy. But let me tell you this. In a scalar form, I'm going to have a summation, you know, and there's going to be a square. But because I'm talking about matrix, okay, instead of me to have a square, I'm actually going to write, you know, y minus that, put a transpose, multiply by that. So this is having that in a matrix form. So what I'm trying to say now is just a summation. If I have summation m squared, for instance, okay, is the same thing as m transpose m in matrix. So we're actually using that idea here. Now, the sum of square error, the residual sum of square error in matrix form is this guy. Okay, and if you take a look at what I'm having here, it's actually looking like, okay, it's like I'm having error I equal y minus the x beta, okay, transpose y minus the x beta. It's looking as if I'm having, you know, if this one is a residual sum of squared, then this is like I'm having e prime e error, okay. If you take a look at from here, y equal x beta plus the error. If I call this equation 1, okay, if I take the expectation of both sides, okay, I have this equation 2, okay. If I want to get the error, if I want to solve for error in equation 1, okay, solving for error, you know, from equation 1, okay, my error is going to be y minus that, okay. This is the error, okay. And if error equal to 1, that, then my residual sum of squared is actually going to be error prime, error transpose error, which is going to be this and this. Now, if I have this and this right now, I'm actually going to expand this. I see the way I'm going to expand it. Y transpose Y. y transpose y transpose x beta. Okay, so I'm actually going to have y transpose x beta, okay, here, minus x beta transpose y, negative, negative, positive, okay, x beta transpose x beta. Look at the way I try to use this to multiply that, this to multiply that. That's what I have, okay. Now, if this is what I have right now, okay, this is going to be, so this guy and this guy, they're going to be the same, okay? Because if I find the transpose here, it's going to be beta prime x prime, okay? So this guy and this guy, they're going to be the same. So if I combine them mathematically, okay, I'm actually going to have beta prime x prime y, okay? Beta prime x prime y. Then here, I'm actually going to have beta prime x beta, okay? If you take a look at, like I said, combining this, okay, that's what I'm going to get. Now, if this is RSS, I'm going to differentiate this guy with respect to beta. This is going to be 0, okay? And here, I'm actually going to have x prime y. Let me just see, 2x prime y. And here, you know, this guy is more or less like beta squared, okay? That's going to be 2. So I'm actually going to have x prime x beta, okay, and you know, the beta squared, then I'm going to have 2, okay, 2. Then I'm going to set this to 0, okay. When I set that to 0, okay, you know, when this one go to the other side, the 2 is going to cancel 2, and when 2 cancel 2, okay, when 2 cancel 2, I'm actually going to have x prime x beta equal x prime y, okay. I'm actually, because like we're in optimization problem, you're going to set to 0, okay, and that's going to be 2, and that's going to cancel that out. So I'm going to have this. Now what I'm going to do, I will pre-multiply both sides, okay, by x, by the inverse of that, okay. So here I'm going to do this, okay, multiply by this, then I have this equal s the this, okay. So right now, when the inverse, when you know, from the fact that if you take a look at this, when inverse multiplied by a is identity, when I have a matrix, so here I'm gonna have identity, okay, s, I'm gonna have this guy s prime y, okay, and identity multiplied by that's going to be beta. So I'm going to call this an estimate right now. I'm going to put OLS equal this. Now, if I want to, this is the formula now. This is an estimator. This guy is going to give me what I'm looking for. It's going to give me beta naught, beta 1, beta 2. I'm actually going to get that, simultaneously. Okay, which is equation 3.10. Okay, I just show you now how to derive equation 3.10. Now, when you have this equation, like I said, this is going to give you these results. It's going to give you beta naught cap, beta 1 cap, beta 2 cap, all the way to beta 2 cap. That is what this guy is going to give you. That guy is in matrix form. Okay, now, for you to be able to understand how we use matrix approach for multiple linear regression, I want us to first start using matrix approach for simple linear regression. Now, please pay attention. I want to use this method. I can use this method depending on the numbers of parameters in my model. I can use this method to obtain beta naught, beta 1 in a simple linear regression. I can at the same time use it to estimate, multiple parameters. Okay, but you know what I want to do right now? Okay, I actually want to show you how we can represent simple linear regression in matrix form. If you understand how to represent simple linear regression in matrix form, then you'll be able to generalize to multiple linear regression, that idea. And that's what I want to show you now. Okay, now let's see what now take a look at this. Now, do you know in simple, since this is the formula, now the question now is, how am I going to get x prime y? What is x prime y? And what is the inverse of x prime s? That's what I want to show you now for simple linear regression. If you don't understand, please ask question. I want to show you right away. Now, if I'm talking about simple linear regression, okay, take a look at this guy. What I have here is x prime x. Before I can get the inverse of x prime x, I need to first get my x prime s. My s prime s for simple linear regression is going to be n number of observation, sum of s, sum of s, sum of s squared. That is s prime s. Okay? Now, of course, if I have this matrix 2 by 2 for simple linear regression, all what I need is to find the inverse. I'm going to get each of these from my data set. Okay, you know, in your data set, you're actually going to have x and y, right? Okay, that, you know, the sum of that, I can also get s squared, y squared, sum of s squared, sum of y squared, and the possibility of what I can get xy, so sum of xy. Okay, now from the data set, you know what to plug in here, and that will give you s prime s. From the data set, how do we get s prime y? Please pay attention. How do we get x prime y? This is s prime y. The s prime y, the first one, summation y, summation xy. Do you see that? Okay. Now, the moment I get that, okay, for s prime s, I find the inverse, and I use the inverse to multiply x prime y, automatically, I'm actually going to get my beta cap. And my beta cap is going to be, I'm actually going to simultaneously estimate the two, the two parameters, the beta naught and the beta 1. Is there any question before moving forward? Any question from anybody? Do not hide your feelings, okay? If you don't understand, ask me question. I'm going to explain that. Okay, now I want to move right now. Okay, I'm going to move right now. I want to talk about this. I want to talk about something. Okay, take a look at this guy. Okay, that guy is more or less like residual sum of squared. Okay, you know the other time that arriving y prime y2 beta prime s prime y plus that. Okay, that is that. Okay, and of course, you know, if you want to have it in a several, you know, this is also showing a different way of figuring it out. This is another way of figuring it out. Okay, now the next, you know, I said something the other time. Statistics is like a story. We've been able to, we understand how to simultaneously estimate our parameters in the simple linear regression model. What is the next thing? After having the model, can I talk about fitted values and residual? You know, without having a model in place, without having your model estimated, you can't talk about fitted. Fitted is predicted. And the moment you talk about fitted, you're going to talk about residual. Because residual will be the difference between the actual and the fitted. Now, I want you to see mathematically what notation we use for fitted. Of course, this is it. You can see y has a cap. That means I want to have a predicted y. I can only talk about predicted response if I have values for my beta naught and my beta 1. And after that, subtracting the predicted from the actual, I'm actually going to get residual. Okay? Now, I want to show something now. Please pay attention. How are we able to get a fitted? Take a look at what I have. Please pay attention. I got this guy, and this is the fitted. Oh, the fitted is the same thing as the average. The fitted is the same thing as the mean function. Okay, the fitted. Please pay attention. The fitted. Okay, if you take a look at what I circle right now. Okay, y cap equal. Okay, if you take a look at that guy. Okay, then it means this is the same as expectation of y, okay, given s. It's the same. So if this is defeated, now, if I have this equal s, and what is my beta cap? You know, we derived that the other time. Recall that beta cap is x prime s inverse x prime y. I'm going to plug in this one inside here. So inside here, I'm actually having this guy, okay, x prime y. Please pay attention to this. Oh, what? This is predicted y. This is the actual y. Then this guy is going to have a name because that guy depends on s. Everything here depends on the data s. I can call that guy, I can write this equal py. Okay, and where p is this guy. And that very p is what we call hat matrix. Hat matrix, or we call it a projection matrix. Okay, now when you take a look at this guy now. Okay, take a look at that now. Okay, and that p is that. Can you see that? We call it hat matrix. What is the function of hat matrix in statistical framework? Hat matrix enable us to transform actual response into predicted response. I'm going to say that again. What is the significance of projection matrix? What is the significance of hat matrix? The hat matrix enable us, okay, to transform actual response into predicted response. Without the projection matrix, without the hat matrix, there is no way we'll be able to transform actual response into predicted response. Because of that, the validity of whatever we're going to be doing here will depend on the properties of hat matrix. Because of that, I want us to work with hat matrix. What is the hat matrix? P. This particular matrix here that we also call projection matrix. I'm going to repeat myself. The validity of whatever we're going to be doing in this area of statistics depends on properties of hat matrix. Because of that, we want to talk about properties of hat matrix. Please pay attention. One of the properties of hat matrix is that it is idempotent. What do I mean by idempotent? When I use P, okay, I said from here. Let me quickly write this. Please pay attention. Okay, we're gonna have some theories in this course. Okay, now the hat matrix P, okay, is X, is this, okay. I said the validity of what we're going to be doing in this area depend on the properties, okay, okay, of hat matrix. Now, one of the properties is that this multiplied by this must give this. we call number one property to be idempotent. Okay, idempotent in a matrix, it means when I use a matrix to multiply itself, it must give itself. Let's verify. This one is P. Multiplied by another one. Okay, this is P multiplied by that. Now, let's take a look at something. This guy is going to cancel this guy because that will give us identity, right? So here, I'm going to have X because this canceled this one. Then I'm going to have X. Then I'm going to have this. What has happened? That gave us back P. Can you see that? That gave us back P. That's an identity. That's an idempotent property. That is the number one property of projection matrix. Number two property is symmetric. Symmetric. Symmetric property. And I said here by symmetrical property, okay, when I actually have a matrix and I find the transpose of a matrix, if it is the same as the matrix, then that matrix is symmetric in nature. Okay, now this is what we're going to do right now. Okay, we want to investigate the second property that we call symmetric. Okay, now the second property, okay, we want to investigate, okay, if I have P, okay, to be XS transpose, the inverse of that, this, okay, and I want to find the transpose of P, okay, which means I actually want to do this. I want to find the transpose. Okay, now if I actually want to find the transpose, if I take this as, maybe I divide the whole thing into this and this. Okay, now, recall that if I have the transpose of this, it's actually going to be this from mathematics. Okay, now here I want to take A to be this guy, B to be this guy, then I'm actually going to write this. Okay, I'm actually going to write this transpose X transpose. Now, if I now take this as two different things now, transpose of a transpose, so this is going to be, so I'm actually going to have X, and transpose doesn't work on inverse, okay, I'm actually going to have this. What am I getting right now? I'm getting back my P. And that shows that, the projection matrix is actually symmetric. Okay, now let me tell you this. When these two properties actually hold, okay, which is what I've already demonstrated that here, okay, that has implication on the error. Okay, now if these two properties hold, okay, if I want to find the error, of course I told you the other time, okay, error is going to be the actual minus predicted, right? As you can see in this form, okay, and of course, as you can see here, which is y minus y cap, okay, and the y cap is s beta cap, okay, and in the end, okay, I'm actually going to have this guy. How? Because the hex beta that I derived the other time is py. Then if I factorize y out, if I factorize y out, okay, I'm actually, I'm going to have, if I, what I'm trying to do is, let me use this. If I have the error, okay, I got the error equal y minus py, okay, I'm going to factorize. This very y is post-multiplying. Post. There's a difference between pre-multiply and post-multiply in matrix. Okay, this is post-multiplying. Okay, so I'm actually going to write identity minus p, then y. Look at that. Don't put this guy here. It's post-multiplying. So I minus p. Now, let me tell you something. If I want everything in statistics, when you are fitting a model, okay, what we tell whether a model is fantastic is the error, okay? But let me tell you this. how can I really know, the properties, okay, that is going to make error to do a great job? Then I need to investigate I minus P. When P is idempotent, when P is symmetric, I minus P must also be idempotent. I minus P must also have that property. You can investigate that. Now, when that hold, okay, then we're going to move forward. Where are we moving forward to? Oh, I want to make an inference about prediction, but I need analysis of the error. When I want to make inference about prediction, I want to know, I actually want to find the average prediction. I also want to find the variance of prediction. We've done that in this class. You remember the other time in this class we talked about prediction, interval for individual prediction and interval for average prediction. Because prediction is a random variable, prediction varies. And therefore, if you take a look at this, I want to find the expected value of y cap. And the expected value of y cap is the expected value of py. Okay, P is the projection matrix. Now, because here P is not a variable, P depends on S. In regression, we know our data S is fixed. The one that is a random variable is Y. So P is going to come out. I'm going to have P expected value of Y. What is the expected value of Y? Is S beta. And what is the B? Then I'm going to write P. This is the P. Okay, let me use this so that you can easily follow. You can easily follow. Please pay attention. Okay, this is what I'm saying. Take a look at this. Y cap equal to Py. If I take the expectation on both sides, expectation will only attract Y. Y is a variable. Okay, X is fixed. Okay, now if I plug in, what is the expected value of Y? Is X beta. When I put that, I'm going to have that. Now, what is P? P is the Arc matrix. Okay, if I plug in P, this is P, right? Can you see that? That is P. Then times X beta. So if you take a look at, if you simplify this one, that will give you only X beta. Can you see that? Which confirm our mean equation. What's our mean equation? Expected value of Y equal to X beta. Now, expected value of Y cap here equal to S beta, what is the variance? This is the variance. The variance is going to be sigma squared P. What is that P? Projection matrix. Okay, I just wanted to take note of that. And when you investigate, take a look at this. I want to show that the expected value of error equal to 0. I have to put into consideration characteristics of projection matrix because it's one of the assumptions. Now, let's see how it's going to happen. Error. What is error? Error is I minus P multiplied by Y. Can you see that? Error is I minus P multiplied by Y. If that happens, expectation will only grab variable Y. I minus P is a cost is fixed. It's going to come out of the expectation. I'm actually having this. Now, what is expected value of Y? We've derived that to be X beta. Now, I minus P multiplied by X beta. I minus P multiplied by X beta. Okay. Now, you're gonna see something now. This multiplied by identity, X beta. Then this multiplied by that, P X beta. Now, this is going to be X beta minus, what is your P? Okay, this is P, right? X, this, X prime, then X beta. This, cancel that. X, yeah, I'm going to have X beta minus X beta. What has happened? We've been able to prove that expected value of error equal to 0 without projection matrix. Okay, following that property, having that property, exhibiting that property, and then we may not be able to prove that the expected value of error equal to 0. Now we can also talk about the variance of the error because error is a random variable. This is the variance of the error is also going to be in terms of sigma square I minus P. Okay, then we can talk about variance of prediction. Variance of the error is different from variance of prediction. This is the variance of prediction. Okay, I just wanted to take a look at that. And this is the variance of the error. All of that, they are in terms of projection matrix. Okay, I quickly, because of my time, I'm going to do this. I think you've done this the other time. This is estimated mean response. If I want to talk about, if I want to get, what is it called? If I want to predict interval estimate for average, you remember we make use of a particular variance the other time. Okay, when you want to do for individual, you remember the individual we're going to have 1 plus, right? Do you see 1 plus? You understand? The other time that we talk about the prediction interval and the confidence interval. Now, what I'm going to do, I will quickly take you to regression model. If I have a regression model with 2 variables, with 1 response and 1, explanatory variable, the design matrix is going to be this. Constant of 1 and just a single variable. This is for y. Okay? If I have that, okay, then I can test that on data set. Let's test that on data set. You give me this data set. Okay? 1, 1, 1, 1, 1, 1 is for constant. This is for variable x. This is for variable y. Okay? How can we use a matrix approach to solve this? Of course, you already know how to do that using R. But how do we use matrix approach? To use matrix approach, okay, I need this formula. I need this formula. I need that formula. How am I going to set it up? Pay attention. Okay. You know, in my data set, I need S prime X, right? The S prime X, I told you the other time, this is the formula. Okay. Now here, what is the number of observation in the data? Sum of S, sum of X, sum of S squared. I'm going to plug that in there. What about my X prime Y? Take a look. S prime Y. S prime Y is summation Y. Okay. I'm trying to say from that data now, okay, summation Y is that. Summation XY is that. But here, S prime S. And I have 23 observation. Sum of S is 66.59. Of course, what I'm going to have is what I'm going to have. The sum of S squared is that. The moment I have this and I have that, I only need to find the inverse of this, then I multiply by this. Then that will give me what I'm looking for. Okay? And you can also program that in R. If you want to program that in R, because some of you may be wondering, how am I going to get the inverse? How am I going to get this in R? If I have a matrix of this nature, 2 by 2, how am I going to get the inverse in R? Okay? Getting inverse in R is going to be solve. Look at that. Solve. Do you see that? Solve A. You see that? Your matrix, this is the matrix, right? This is the S prime S. Okay? You solve A. That will give you the inverse. And the moment you get the inverse, you just multiply by the X prime Y, by another matrix. And when you do that, you go finally. So just look at what I'm doing here. Finally, look at this. T1 is the inverse of S prime S. Multiplication of matrices now, we have to have this, we have to write this one. Your B is S prime Y. Then when you do that, you have these 2 results. Do you know these 3 results? This is beta naught, this is beta 1. Done. Any question with that? I know today is a serious mathematical, but that's okay. In case you don't understand this, please visit with me during my office hour. My office hour is conducted remotely. Every Tuesdays and Thursday. Please check the canvas. You can be anywhere in the world to join my office hour, because in the test and exam, it's going to be a combination of R knowledge and theoretical knowledge. So, and that's why if an area is not clear, please reach out. I want to hear from you. That's all what I got for you today. Make sure you all stay safe and have a lovely day. Bye for now, everyone.